Girl, I can change your life, but you heard it all. I know you heard it all. I'm from the city. Hey y'all, Dumb Nerd here. Today I'll be doing a review for Unit 5. All credit goes to Prepworks Education on YouTube. The MVT states that if we have a function f that is continuous over the closed interval a to b and differentiable over the open interval a to b, there must be a point where the derivative equals the average rate of change. The extreme value theorem, or the EVT, guarantees that a function f has at least one minimum value and at least one maximum value on the closed interval from a to b. The global max or min is the highest or lowest point on the function over a closed interval, while a local max or min is simply higher or lower than points directly to the left or the right of it. Think of it as hills or valleys. A critical point is defined as any point where the derivative equals 0 or the derivative is undefined. All local extrema occur at critical points. When the first derivative is positive, we know that f of x is increasing. When the first derivative is negative, we know that f of x is decreasing. When f of x goes from increasing to decreasing, we know we have a local max, so therefore, when the derivative goes from positive to negative, we have a local max. The opposite goes for local min. Global extrema only occur at endpoints or critical points, but you need to check both. For example, say we want to find the global max of f of x equals x squared plus 4x plus 4 over the interval of 0 to 4. First, check the endpoints and find that f of 0 is 4 and f of 4 is 46. And then we check the critical points, which we get by setting the first derivative equal to 0. After we compare all the endpoints and critical points, we find that the global max is at x equals 4 because f of 4 equals 36, which is higher than all the other endpoints and critical points. The second derivative of a function determines its concavity. When the second derivative is negative, this means the first derivative is decreasing and the function is concave down. On the other hand, when the second derivative is positive, the opposite is said. When f changes concavity or when the second derivative changes signs, there is a point of inflection. The second derivative test is another way to classify critical points. Whenever we have a local maximum, we know that the graph is going to be concave down like a hill, and whenever we have a local minimum, we know that the graph is going to be concave up like a valley. So given a point C is a critical point, if the second derivative is negative or the graph is concave down, we have a local max, vice versa for the second derivative being positive. Above are the 7 steps to success for optimization problems. If you follow these steps, you should be able to ace these problems. I apologize for the late upload, and the 6th review should be out by, Dumb Nerd out.